Welcome, ladies and gentlemen, to Integrated Math 2. In today's episode, we will be discussing Chapter 5.2.1, which is perfect square equations. They do reference 5-59, which is kind of an intro to this type of thing, but we've actually been introduced to this in a different way, and I'd like to call on that way because I think it will make more sense to you. In Part A, we're being asked to solve the equation of x minus 1 squared equals 4. Now, in this case, back in Integrated 1, we learned a method of solving called looking inside. So I'll go and just use that method first, looking inside. And basically what looking inside was telling us was to infer what number would make this true. Now in this case, I'm trying to get the inside to become a number so that when I square that number, I get 4. So there's only two possible options here. I could either have the inside be, the inside in total, right? The inside in total could either be a 2, because 2 squared is 4, or the inside could be a negative 2, because negative 2 in total squared is 4. So if I wanted the inside to be a regular 2, then what would x have to be to make that happen? Well, x would have to be 3, right? If that was the case, because 3 minus 1 is 2, 2 squared is 4. What could x also have been? X could have been negative 1, right? X could have been negative 1 because negative 1 minus 1 is negative 2, and negative 2 in total squared is 4. So that's the looking inside method. We will deal with another method later on in this section, but for now, let's just stick to looking inside. In B, x minus 1 squared is equal to 0. And so anything squared becoming 0, I think there's only one option in this case. I think x can really only be 1 because I can't make the inside negative or the inside positive like I did in the last problem. So hopefully just x being 1 is good enough of an explanation. And then in the last one, C, we got x minus 1 squared equaling negative 4. Now, if you really, really think about it this way, I can't think of any number that which I square it becomes a negative value. Like, I just don't think it exists. Even if I plug in negative a trillion, right? Negative a trillion minus 1 is negative a trillion and 1, but if I square it, it automatically becomes positive. So I don't think there's anything. This is no solution. There's no x value that makes this thing true. So, nice little review of Integrated 1 right there. We will learn a new technique for how to deal with these because right now the looking inside method is really good when you have perfect squares emerging on the right side, but as we will see in a little bit, that will not always be the case. So I'll be back with the next problem. In 5-61, it says the quadratic equation x minus 3 quantity squared is written in perfect square form. And that is because the expression x minus 3 squared, well, we know this. This is the factored version of a perfect square trinomial, right? And in its trinomial form, this was x squared minus 6x plus 9. So hopefully that makes sense. And the reason why it's called a perfect square is because when you build this thing with algebra tiles, it actually does make a square. And so, the name definitely has origin. So it says, now solve this idea here. So x minus 3 squared equals 12. So unlike the last problems, I can't use looking inside because I don't know of any number that when I square it, it automatically becomes 12. So what I'm going to do is I'm going to go ahead and square root both sides. And I'm going to square root that because it's the inverse operation of the x minus 3, or of the squared, which then releases the x minus 3. And what I get is the square root of 12. Now from here, I'm going to do something a little bit odd. I'm going to refer back to that last problem that we did, which was x minus 1 squared. So x minus 1 squared equaled 4. And when I did the looking inside method, I knew that the two things in the inside that had to be true were that x had to be a number such that the inside would end up becoming a 2 or a negative 2. Hopefully you remember that from the looking inside method. Now, if I go ahead and square root both sides, then I'm going to say x minus 1 is equal to 2. But remember, the inside needs to be either the positive version of itself or the negative version of itself, which is why this 2 here, which is a representation of what is supposed to be on the inside now, will become either the plus version or the minus version. And then if I split it up, and I say x minus 1 is equal to negative 2 and x minus 1 is equal to positive 2, if I add 1 on either side, I will get x equals negative 1, which I believe was the answer the last time we did this, using the looking inside. Or x would equal 3, using the looking inside method again. I feel like we got that both times, negative 1 and positive 3. Why am I bringing this up? It's because when I take the square root of this 12 here, and I'm doing it in the midst of cancellation of the squared, that rad 12 is going to get a plus or minus. And so now from here, I'm going to go ahead and add 3 to each side. And so what I get is x equals 3 plus or minus rad 12. Now, I'm going to actually split this thing up, and I'm going to say, look, there are two answers at play here. 3 plus rad 12 and x equals 3 minus rad 12. Now, for those of you out there who are saying, yes, you can simplify the square root of 12, I know you can. I will go over that in a different lesson. But for now, I'll go ahead and leave the answer like that. The bigger idea here is that when you square root something in the middle of an equation, there needs to be a plus or minus version of the square rooted section. And there are other reasons for that, which you will learn in Integrate 3. We might even get into them in this class. But for now, that plus or minus is there because of the whole looking inside method, where the inside had to be the positive version of the square root or the negative version of the square root. And so here you go. That's A. B, we notice that there are two solutions. Two solutions. Because 3 plus the square root, 3 minus the square root. Now it says the solutions from part A are considered irrational. And so they are decimals that can never repeat and never end. We will write these in decimal form. Okay, so that is going to end up becoming 3 plus rad 12 will be 6.464, and then 3 minus rad 12 will be negative 0.464. And there you are in decimal form. So that is a perfect square equation. Let's go ahead and pause. I'll come back with the next set of problems here. So in 5-62, it talks about the number of solutions, and sometimes you have two solutions, sometimes you have one solution, sometimes you have no solutions. Let's see if we can find out a pattern of when that happens. So in part A here, we're looking at 2x minus 3 squared is equal to 49. So rather than doing the looking inside method, I'll go and get us used to finding the square root on either side. So I end up getting 2x minus 3 equaling the square root of 49 is 7. But remember, I just took the square root of an equation, right? So again, that whole looking inside necessitates that it's plus or minus 7. And so from here, I'll go ahead and I'll separate out a different way, make some more space that way. So it's 2x minus 3 equals negative 7, and 2x minus 3 equals positive 7. So if I add 3 on either side, I'm going to get 2x equals, looks like negative 4, divide by 2, and I get x equals negative 2. By adding 3 to either side, I get 2x is equal to 10. Dividing by 2, x is equal to 5. So I got two solutions on this one. So again, let's just make a note of that. Two solutions. Awesome. Now B, 7x minus 5 squared equaling negative 2. Now, whether you have a calculator or not, if you attempt to square root on either side, you will get no solution. You'll get an error in your calculator. But that should hopefully make sense, because if I go back a couple steps here, what number can I plug in here that when I square it, I get a negative value? Nothing. So this is no solution. Hopefully you're starting to see a pattern there when no solution starts to become a thing. And then in C, we got x plus 4 squared is equal to 20. I see no issue in square rooting either side, so I get x plus 4 is equal to, again, I took the square root of an equation, right? The looking inside method necessitates a plus or minus rad 20. So I'll go ahead and subtract 4 from either side, and I get x equals negative 4 plus or minus rad 20, which then can be split up as negative 4 plus rad 20, negative 4 minus rad 20. So again, two solutions here. Two solutions here. There's two. Okay, let's take a look at D real quick. D, is, actually, I'm running out of space, so I'm going to go ahead and delete this mumbo jumbo here. Actually, you know what I'm going to do? I'm going to pause for a second. I'm going to put it up towards the top of the board. Give me a second. So I wanted to leave those there. That way I could compare them when all is said and done. But let's take a look at D. If I do D and I get 5 minus 10x squared is equal to 0, if I square root on either side, I get 5 minus 10x equaling 0. Not plus or minus, because 0 is neither plus nor minus. So I'm going to go ahead and add the 10x to either side. So I get 5 equals 10x, divide both sides by 10, and I get x equals 5 over 10, or 1/2. So in this case, I only got one solution. One solution. Right? Now notice what the perfect square equation equaled when I got one solution. Notice what the perfect square equation had to equal when I got two solutions, when I got no solution. Hopefully that's starting to make sense. And with E, I'm hoping you can beat me to this answer. If not, feel free to pause and conjecture what's going to happen. But we have a perfect square equation, something being squared equaling a negative value. And I believe that is none. No solution. Oops, no solution. Not none solution, no solution. F is going to be x plus 11 squared plus 5 equals 5. Let's go and get the perfect square equation by itself. So I'll go and subtract 5 from either side. And I get x plus 11 squared equaling 0. Square rooting either side, I get x plus 11 equals 0. Again, 0 is neither positive or negative, so I don't think I need to include that plus or minus. After subtracting 11, I get x equals negative 11. Only one solution here. So at this point, let's try and make a generalization. If our perfect square equation is equal to a positive, we get, try and beat me to this answer here, we get, we get two solutions. If our perfect square equation is equal to 0, we get, try and beat me to it, one solution. And if our perfect square equation is equal to a negative number, or equal to a negative, we get, try and beat me to it, no solution. So that is the generalization that you need to be able to make when you run into these perfect square equations. And eventually we'll be dealing with these perfect square equations a lot. So I want to get used to seeing those patterns now. As always, please leave comments or questions in the comments area, and I will see you all in the next episode.